Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Department of Physics, Central University of Haryana. Today, we are going to discuss about a module, connection between ket vectors and wave functions, continuity equation and conservation of probability from the paper Quantum Mechanics 1. After studying this module, you will be able to know the connection between the ket vectors psi as a function of time t and the wave function psi as a function of position vector r and time t. You will also learn how to set up the Schrodinger equation expressing the time development of the wave function using the Hamiltonian operator. You will learn the meaning of probability current density and how to express it in terms of the continuity equation. You will also be able to appreciate the significance of continuity equation with the help of few examples. Having learnt that the state of a particle is represented by a wave vector in the state space denoted by the ket vector psi as a function of time t, our first objective in this module is to establish its connection with the wave function psi as a function of position vector r and time t, representing the position of the particle r at an instant of time t. Introducing the Hamiltonian operator corresponding to the dynamical variable energy comprising, as in classical mechanics, the kinetic and potential energy parts, we then set up the Schrodinger equation expressing the time development of the wave function. As a next step, we discuss some general properties such as probability current density, continuity equation, and study a few examples to appreciate the significance of continuity equation, connection between ket vectors and wave functions. Now, let us study the connection that is there with wave mechanics. So, for studying that, let us start with the state vector ket vector r, which represents the state of space of a particle in 3 dimensions. That means that this ket vector r actually represents the position of the particle in 3-dimensional space. Now, the set of ket vectors r are the common eigenvectors of the 3 Hermitian operators, that is, the operator x, the operator y, and the operator z, which correspond to the dynamical variables x, y, and z respectively. So, what we can understand is that for each of the eigenvectors r, there are 3 Hermitian operators that correspond to each of these 3 eigenvectors and that also correspond to the dynamical variables x, y, and z. So, if you write it in mathematical form, then the equation that you get is that the operator x acting on the ket vector r gives us the dynamical variable x and the ket vector r, that is the eigenvalue x and the ket vector r. Similarly, the operator y acting on the ket vector r gives us the eigenvalue y and the ket vector r, and so on for the z-axis. You get, or rather the z dimension, you get that the operator z acting on the ket vector r gives us the eigenvalue z with the ket vector r. So here what we see is that the operators x, y, and z commute pairwise as they have a common basis of eigenvectors, and the normalization of the ket vectors r is such that if you take the normalization of the bra vector r with the ket vector r prime, then this gives us the delta function delta r minus r prime, which means that unless r prime vector is equal to r vector, the normalization will give us 0, and if r prime vector is equal to the r vector, then we get normalization as 1. And this can further be expanded mathematically along the three dynamical variables, or with respect to the three dynamical variables, as delta function of x minus x prime times delta function of y minus y prime times delta function of z minus z prime, which means that the vector r minus r prime, that was the delta function of vector r minus r prime, can now be expanded in the form of, or in terms of, the three dynamical variables. And again, if x is equal to x prime and y is equal to y prime and z is equal to z prime, then we get a value 1, else we get a value 0. So in a similar manner, one can also define the closure relation for the ket vector r as integral over dr, that is integral over the volume, ket vector r, bra vector r, which basically depicts the closure relation, and this comes out to be equal to the identity matrix I, or the identity operator I. Connection with wave function. Now let us study the connection with the wave functions. So let us consider three Hermitian operators denoted by operator px, py and pz, which denote the vector p corresponding to the dynamical variables x, y and z components. That is, that for the vector p, the Hermitian operators px correspond to the dynamical variable of the x component, the operator py corresponds to the dynamical variable of the y component, and the operator pz corresponds to the dynamical variable of the z component, where the corresponding dynamical variables are given by px, py and pz respectively. That means px is the dynamical variable of the Hermitian operator px, py is the dynamical variable of the y component of the Hermitian operator py, and pz is the dynamical variable of the z component of the Hermitian operator pz. And the vector p represents the momentum of the particle. So their matrix element in the space basis, or in the basis of the ket vector r, are given by the expectation value of the operator p, or the vector p. So we write the expectation value as bra vector r, vector p, ket vector r prime, and this turns out to be equal to minus iota times h cross del operator r, delta function of vector r minus vector r prime, where h cross is equal to h by 2 pi, and h is the Planck's constant, and the del operator r basically denotes the del operator with respect to the position coordinates, and the delta function of vector r minus vector r prime denotes that unless and until vector r prime is equal to vector r, the delta function will return a value 0. And if the vector r is equal to vector r prime, then the delta function returns a value 1. Next, we come on to the commutation relation between the components of the vector p, that is the momentum vector p, and the components of the position vector r. And let us see what are the commutation relations for these. So if you look at the commutation relation for the position vector r, then the commutation relation of operator xi xj is equal to 0 if I is not equal to j, and the commutation relation of the operator pi and pj also comes out to be 0, while the commutation relation of the operator xi with the operator pj is equal to iota times h cross times delta ij times the identity operator, or the identity matrix, where delta ij is equal to 0 if I is not equal to j, and is equal to 1 if I is equal to j, for I and j running from 1 to 3. So in this manner, we have defined the commutation relation for the position operator as well as for the momentum operator. Now the momentum operators have their eigenvectors in momentum space, which is denoted by the ket vector p. So the manner in which we had earlier defined the relation for the relation between the operators and the vectors and the dynamical variables for the position coordinates, in a similar manner, here we are defining the relation between the momentum operator, the momentum vector, and the dynamical variable of the corresponding operation. So along the x component, we have that the operator px acting on the ket vector p gives us the dynamical variable px with ket vector p, where x indices denotes the x component of the momentum vector, or similarly the operator py, which is the y component of the momentum operator, acting on the ket vector p gives us the dynamical variable py acting on the ket vector p. And similarly for the z component of the operator momentum operator, that is operator pz acting on the ket vector p gives us the dynamical variable pz acting on the ket vector p, where again we have the normalization condition given by bra vector p ket vector p prime is equal to delta vector p minus vector p prime, which is equal to 1 if vector p is equal to vector p prime and is equal to 0 if vector p is not equal to vector p prime. So it's a delta function that defines the normalization condition for the momentum operator also. So in this manner, we can see that we have similar relations for the momentum operators as well as for the position operators. So we continue our discussion with the connection between the wave function and the operators. So now let us come on to the relation between the ket vectors for the position and the momentum. And since we've already discussed earlier the various commutation relations for the position operator and the position vector and the momentum operator and the momentum vector, therefore now we can come to defining the relation between the position vector as well as the momentum vector. So if you look at the mathematical equation, bra vector r ket vector p turns out to be equal to bracket open 2 pi h cross bracket close whole to the power minus 3 by 2 times exponential to the power iota by h cross vector p dot vector r. So this gives us the relation between the ket vector p and the ket vector r. Having defined this relation, we are now in a position to define our Hamiltonian operator, which has both the kinetic energy term as well as the potential energy term. And the Hamiltonian operator, H operator, is given by operator H is equal to operator P whole square by 2m plus V as a function of vector r and time t. So here the vector operator P is the momentum vector, m denotes the mass of the particle, and V is the potential energy, which is a function of both the position as well as time. So now if you want to define the state of a particle at any time, then it is represented by a vector in the state space by the ket vector psi as a function of time t, and the wave function, which is given by psi as a function of vector r and time t, is the component of the ket vector psi t on the ket vector r. That is, we can write the complete wave function psi as a function of vector r and time t is equal to bra vector r ket vector psi as a function of time t. Having defined these relations for the complete wave function as a function of both position and time in terms of the position vector and the wave function or the ket vector psi t, we are now in a position to define our scalar products between two different ket vectors for the wave function. So let us consider two ket vectors for the wave function. One is ket vector phi and the other is ket vector psi. So the scalar product of the ket vector phi and ket vector psi are defined as bra vector phi, ket vector psi, which is the scalar product of phi and psi, and this is equal to integration over the volume dr vector times scalar product between bra vector phi, ket vector r times scalar product between bra vector r, ket vector psi. And this turns out to be equal to integral over the volume dr vector times phi star as a function of vector r, psi as a function of vector r, where phi star as a function of vector r is the complex conjugate of the function phi. And here we have used the closure property for the position vector r to reach the final relation. The action of the operators r, that is the position operator, and the momentum operator p, and the Hamiltonian operator h on the ket vector psi as a function of t can be expressed in terms of the wave function as bra vector r, operator r, ket vector psi as a function of t, and this is equal to vector r times the wave function as a function of position vector r and time t. So this is the first relation that we get when of the ket vector psi as a function of t when r operates on it. In a similar manner, we can also define the wave function when the operator p, that is the momentum operator, acts on the ket vector psi as a function of t. So writing that in mathematical form, we have bra vector r, momentum operator p, ket vector psi as a function of t, and this turns out to be equal to minus iota times h cross del operator wave function psi as a function of position vector r and time t. Here h cross is h by 2 pi and h is the Planck's constant. And finally, in a similar manner, we can also define the expression of the wave function in terms of the operator, Hamiltonian operator, that is when the Hamiltonian operator is acting on the wave function ket vector psi t, and this can be written as bra vector r operator h, which is the Hamiltonian operator, acting on ket vector psi as a function of t, and this turns out to be equal to minus h cross square by 2m times del square operator time acting on the wave function psi as a function of position vector r and time t, plus the potential energy term, that is the potential energy function v as a function of position vector r and time t acting on the wave function psi as a function of position vector r and time t. So this defines our complete Hamiltonian operator acting on the wave function ket vector psi t. Schrodinger equation. Now, the modulus of the square of the normalized wave function, that is mod of square, rather I should say square of the mod of the wave function psi as a function of position vector r and time t, gives the probability density of finding the particle located at the position vector r at a particular time t. So in this manner, by using the square of the modulus of the wave function, one can actually find out the probability density of finding a particle in a localized region defined by the position vector r at a particular time t. Now, since the wave function is a function of both the position vector r and time t, therefore the time development of the wave function is given by the Schrodinger equation, which can be written as iota times h cross partial derivative of the wave function psi as a function of position vector r and time t with respect to time is equal to minus h cross square by 2m times del square acting on the wave function psi as a function of position vector r and time t plus the potential energy term as a function of position vector r and time t acting on the wave function psi as a function of position vector r and time t. So this equation represents the Schrodinger equation in the time development form and is popularly called as the time-dependent Schrodinger equation. Now, if the potential energy term does not depend on time, that is, the function v as a function of position vector r and time t is independent of time, does not change with time, then the Schrodinger equation has particular solution of the form the wave function psi as a function of position vector r and time t is equal to wave function psi e as a function of position vector r times exponential to the power minus iota by h cross whole times et, where the wave function psi e as a function of position vector r satisfies the eigenvalue equation of the Hamiltonian operator, which mathematically can be represented as minus h cross square by 2m del squared acting on the wave function psi e as a function of position vector r plus the potential energy v as a function of position vector r times the wave function psi e as a function of position vector r is equal to the energy eigenvalue E times the wave function psi E as a function of position vector r, which means that if the potential energy term is independent of time, then we can do a separation of variable for the wave function, and the position dependent component or term of the wave function represented by psi E as a function of position vector r completely satisfies the eigenvalue equation of the Hamiltonian. Conservation of probability. If a particle is described by a wave function psi as a function of position vector r and time t normalized to unity, then the probability of finding the particle at time t within the volume element given by the position vector dr, which is equal to dx, dy, dz, where dx, dy and dz are the elements or the length components along the x, y and the z axis about the point given by the position vector r is equal to x, y and z. Then the probability is given by, that is the probability density is given by p as a function of position vector r and time t times dr vector is equal to square of the modulus of the wave function psi as a function of position vector r and time t times position vector dr, so that the function, that is the probability density function p as a function of r and time t is equal to square of the modulus of the wave function, which is a function of position vector r and time t. This represents the probability density. If the particle is confined within a given volume, then at any arbitrary time t, the wave function can be chosen to satisfy the normalization condition given by volume integral over vector dr of square of the modulus of the wave function psi as a function of position vector r and time t, where the integral extends over all space. Hermitian, Hamiltonian and probability conservation. Let us now see that how does the probability density change with time. So the interpretation of the square of the modulus of the wave function as position probability density requires that the probability is conserved. That means that the probability of finding the particle enclosed in a given space must remain unity as time changes. So physically what this means is that if we are considering a particular volume and a particle is present inside that volume, then the probability density of finding that particle inside that volume at all times should remain unity. even as the time changes, and therefore the normalization integral must be independent of time. So mathematically this can be written as that derivative with respect to time, that is taking the partial derivative with respect to time of the integral of the probability density p as a function of position vector r and time t integrated over the entire volume vector dr gives us 0. This condition, requiring the conservation in time of the normalization of the wave function, also implies that the Hamiltonian of a particle in a real potential is a Hermitian operator. That means that the Hamiltonian, when operating on the wave function, will return real eigenvalues, real energy eigenvalues. Now let us see how this can be shown. So let us consider the partial derivative with respect to time of the volume integral of the probability density function, that is p as a function of position vector r and time t, and this can be written as equal to the partial derivative with respect to time of the volume integral acting on the square of the modulus of the wave function as a function of the position vector r and time t, and this can then be written as the volume integral over the vector dr within brackets wave function psi star times the partial derivative with respect to time of the wave function psi plus the wave function, the partial derivative with respect to time of the wave function psi star times the wave function psi. So here what one has done is that one has taken the partial derivative with respect to time inside the integral, because the integral is independent of time, so one can do the interchange between the partial derivative and the integral, and taking the partial derivative inside the integral, it acts on the wave function, rather the square of the modulus of the wave function, which can be represented as, or rather written mathematically as, the product of the complex conjugate of the wave function times the wave function, that is psi star times psi. So basically we can expand the partial derivative with respect to time of the square of the modulus of the wave function as acting on the product of the complex conjugate of the wave function psi star times the wave function psi, and this will give us the result that we can see. And when you further solve this in terms of substituting it with respect to the Hamiltonian operator, then the final result that comes out is equal to 1 upon iota h cross whole times the volume integral of over vector dr acting on within brackets wave function psi star times the Hamiltonian operator h acting on wave function psi minus the Hamiltonian operator h acting on wave function psi star whole times the wave function psi. And this above condition, rather the above equation, will lead to the following condition, that is the volume integral over vector dr of the wave function psi star times the Hamiltonian operator acting on wave function psi is equal to the volume integral over vector dr of the Hamiltonian operator h acting on the wave function psi whole complex conjugate times the wave function psi. And this result comes out because we know that the normalization integral is independent of time. So this condition that we have just discussed requires that the Hamiltonian has to be a Hermitian operator. That means that it will always give real eigenvalues. Equation of continuity. Now, using the condition of probability conservation, we find that the partial derivative with respect to time of the volume integral over the probability density function as a function of position vector r and time t is equal to the partial derivative with respect to time of the volume integral dr vector over the square of the modulus of the wave function psi as a function of position vector r and time t, and this can then be written as the volume integral over dr vector acting on the wave function psi star times the partial derivative with respect to time of the wave function psi plus the partial derivative with respect to time of the wave function psi star times the wave function psi, where psi star denotes the complex conjugate of the wave function psi. For time dependence of the wave function, that is, when we want to study the time dependence of the wave function, that is the wave function psi as a function of position vector r and time t, we can use the equation minus iota times h cross times partial derivative with respect to time of the wave function psi star as a function of position vector r and time t, which is equal to minus h cross square by 2m times del square operator acting on the wave function psi star as a function of position vector r and time t plus the potential energy function as a function of position vector r and time t times the wave function psi star as a function of position vector r and time t. So from this, what we understand is that if we want to study the time dependence of the wave function, we consider the time dependent Schrodinger equation, and assuming that the potential energy function is real, we can introduce the following equation. That is, assuming that the potential energy function is real, we can write the above equation as partial derivative with respect to time of the volume integral of the probability density function p as a function of position vector r and time t is equal to iota times h cross by 2m whole times the volume integral over dr vector acting over bracket open psi star times del square operator acting on wave function psi minus del square operator acting on wave function psi star whole times the wave function psi, where psi star denotes the complex conjugate of the wave function psi. H cross is equal to h by 2 pi, where h is the Planck's constant and m is the mass of the particle. From this definition, we can introduce the current density vector, which can be given by, so solving it further, we have iota times h cross by twice m whole times the volume integral over position vector r dr acting on the del operator dot, that is the scalar product of the del operator with respect to bracket open wave function psi star times del operator acting on wave function psi minus del operator acting on wave function psi star times psi whole bracket close, and this entire term within the bracket can be written as vector j. So the equation then transforms to minus volume integral over vector dr del operator dot j vector, where dot denotes the scalar or the dot product, and here the j vector denotes the current density vector, which can be defined as the current density vector j as a function of position vector r and time t is equal to h cross by twice iota times m whole times bracket open psi star times del operator acting on wave function psi minus del operator acting on wave function psi star times wave function psi whole bracket close. And using this definition of the current density vector, we can then rewrite the above equation denoting the condition for probability conservation as volume integral over vector dr of bracket open partial derivative with respect to time of the probability density function p as a function of position vector r and time t plus the scalar product of the del operator with the current density of vector j, that is the divergence of the current density vector j bracket close is equal to 0. So here, in order for this equation to be valid, we have two possibilities. One, that the volume integral goes to 0, that is the volume integral over dr vector goes to 0, but this will lead to a trivial solution. So the only physically viable and significant solution to this equation is that the terms within the integrand go to 0. And this gives us the equation of continuity, which is given by partial derivative with respect to time of the probability density function p as a function of position vector r and time t plus the divergence of the current density vector j is equal to 0. Probability current density. We derived in the previous slide the equation of continuity similar to the one that we encounter in hydrodynamics, expressing conservation of matter, or in electrodynamics expressing charge conservation. Here, any increase or decrease in the probability conservation or in the probability density is compensated by the corresponding decrease or increase through an inflow or outflow of probability current density, that is, the divergence of the current density J times d tau times dt across the boundaries of the volume element. Here it is important to note that the probability current density denoted by the vector j can also be expressed as vector j as a function of position vector r and time t is equal to the real part of the wave function psi star, which is the complex conjugate of the wave function psi, times h cross by iota times m whole times del operator acting on the wave function psi. Since the operator h cross by iota times m times del operator represents the momentum vector p by m, we interpret it as the probability current density. Box normalization and probability conservation. Now, using the Gauss's divergence theorem, one can convert the volume integral to the surface integral. That is, one can convert the volume integral of the divergence of the current density operator into the surface integral of the current density function dot the ds vector, that is the scalar product of the current density function and the surface vector. Using this relation, one can rewrite the equation of continuity as partial derivative with respect to time of the volume integral of the probability density function dr vector with the probability density function p as a function of position vector r and time t is equal to minus surface integral of the current density vector j dot the surface vector ds, where the vector j is the current density vector and the dot denotes the dot or the scalar product. Now let us consider the example of box normalization with the probability conservation. So let us consider a particle enclosed in a cubical box with the edges of side L parallel to the x, y and z axes. That means we consider a box which has edge length L along all the three axes, that is the x, the y and the z axis. And we define the wave function as u k as a function of position vector r is equal to 1 upon L to the power 3 by 2 whole times exponential of iota vector k dot vector r, where the 1 upon L to the power 3 by 2 is the condition that one gets because of the normalization constant. So if you use the normalization condition and apply it to the wave function defined above, then the normalization condition within the box can be given as the volume integral over dx, dy, dz over square of the modulus of the wave function u vector k as a function of vector r is equal to the volume integral over dx dy dz by L cube, and this turns out to be equal to 1. Here we can't use the boundary condition wave function psi as a function of position vector r and time t going to 0, as the position vector r goes to infinity. Rather, we require wave functions to be periodic on the walls of the box being considered. Example: probability conservation in a box. Now let us consider an example of probability conservation in a box. So for doing this, we know that if x or y or z, that is the position along the x-axis or the y-axis or the z-axis, is increased by L, which is the edge length of the box, then the wave function should remain unchanged. That means that whatever is the value of the wave function on one end of the wall of the box should be the same as on the other end of the wall of the box along a particular axis. So mathematically, this can be written as exponential to the power iota times kx times L is equal to exponential to the power iota times ky times L is equal to exponential to the power iota times kz times L is equal to 1, where kx, ky and kz are the x, y and z components of the vector k, and this condition requires that the kx, ky and kz should be integral multiples of 2 pi by L, where L is the edge length of the box, for the relations to be satisfied. Thus, the vector k can be written as vector k is equal to 2 pi by L unit vector n, where or the vector k can be written as vector k is equal to 2 pi by L operator n, where operator n has the x, y and z components given by nx, ny and nz respectively, such that nx, ny and nz take the values 0, plus minus 1, plus minus 2 and so on. That means the components nx, ny and nz of the n operator take integral values. This means that the momentum vectors admissible under the boundary conditions get quantized for the particle in a box. So what we need to understand over here is that when the wave vector k is defined as 2 pi by L times the n, where n is an integer, then this means that the momentum vectors are quantized. That means they can only change by an integral multiple of 2 pi by L. Their values can only change by an integral multiple of 2 pi by L. Now let us consider a particle in one dimension having a wave function with a simple superposition of two de Broglie waves, that is u is equal to a1 times exponential to the power iota times within bracket k1x minus omega 1t minus alpha 1 bracket close, plus a2 times exponential to the power iota times bracket open k2x minus omega 2t minus alpha 2 bracket close, where a1 and a2 are the amplitudes of the wave function of the two de Broglie waves, and alpha 1 and alpha 2 are the phases of the two de Broglie waves respectively. So the position probability density is given by the square of the modulus of the wave function u, which mathematically can be written as the position probability density p is equal to a1 square plus a2 square plus twice a1 times a2 times cos of bracket open k1 minus k2 bracket close times x minus bracket open omega 1 minus omega 2 bracket close times t minus bracket open alpha 1 minus alpha 2 bracket close whole bracket close. Requirement for probability conservation. Now, if the particle is confined to a box, the conservation of probability within the box requires that the integral of the probability density function along a particular direction, that is over the x-axis, going from minus L by 2 to plus L by 2 should be time independent. This means that the following condition must be satisfied, which is that the integral over dx going from minus L by 2 to plus L by 2 of within brackets bracket open k1 minus k2 bracket close times x minus bracket open omega 1 minus omega 2 bracket close times t minus bracket open alpha 1 minus alpha 2 bracket close. And this should be equal to, if you solve the integral, the final answer that one gets is 2 upon within brackets k1 minus k2 whole times sine of within brackets half times L times bracket open k1 minus k2 bracket close whole bracket close times cos of within brackets bracket open omega 1 minus omega 2 bracket close times t minus bracket open alpha 1 minus alpha 2 bracket close whole within brackets. This equation should be time independent. Now, in order for this equation to be time independent, one sees that if the sine term in this equation goes to 0, then this can be done. That is, the term bracket open k1 minus k2 bracket close whole times L is equal to 2n pi, where n is an integer. Thus, the admissible values of n are integral multiple of 2 pi by L, a requirement to ensure the conservation of probability. So students, now let us summarize what all we have learned in this module. So first of all, we have understood the connection between the state vector represented by the ket vector psi as a function of time t and the wave function represented by the function psi as a function of position vector r and time t. Understanding this connection between the state vector psi as a function of time t and the wave function psi as a function of r and t, then we are able to learn how we can set up the Schrodinger equation expressing the time development of the wave function using the Hamiltonian operator. Having done that, then we have also learned the meaning of probability current density and how we can express it in terms of the continuity equation. Very similar to what we encounter in electrodynamics or hydrodynamics. And finally, we appreciate the significance of the continuity equation with the help of few relevant examples. Thank you.